All right, how's everybody feeling today? Bless you. Bless you. Let me get one more thing out of my office. I almost forgot.
Is it actually like I know.
All right. Anyone have any questions or need anything before we get started? All right. Welcome back to class. I hope breaks were excellent all around. Let me load up the calendar real quick so I can point at a few things, and then we'll get started. Reminder of some scheduling details, since it's been a week since I saw you, technically. Today is Wednesday, April 3rd. There is no lab this week at all, because Monday did not exist. We have normal class meetings for the foreseeable future. I want you to note, though, that next Monday, April the 8th, is Eclipse Day. There's a big eclipse that's going to be happening. This particular area will not be in the path of totality. This area should only get about 75% totality. But it's still a big deal. This is a pretty rare kind of eclipse, especially considering we had a similar one 6 years ago. These happening in pretty close succession is pretty interesting. I plan on lecture that day being fairly eclipse themed. I'm going to talk about gravity and orbit on that day. And we will not have a normal lab next week because I want everyone to be able to take Monday afternoon to view the eclipse if you have the time and want to do so. It'll take place Monday afternoon. The sky will start getting darker around 1 p.m. We'll get max totality for this region around 3:30, and then it'll get brighter again until we return back to normal. That's how I understand the schedule last I checked. Now, just like you shouldn't stare at the sun, you also shouldn't stare at an eclipse unless you've got these. I'm giving out eclipse glasses. To make sure they work, you want to hold them up to the light and make sure you see nothing. These block out 99.9% of all light, which is why they are safe to view the sun through them. So if you want to view the eclipse, make sure you have a pair of these. They are here at the front. Come grab one. Preferably only one a piece, though. I want to make sure everyone gets a chance to grab a pair. So, we're going to do eclipse stuff on Monday. No in-person lab next week, so you don't have to report anywhere. If you want to view the eclipse, you're free to just do so on your own time. I will instead post an out-of-class assignment for lab next week that'll involve the math about eclipses in orbit that we'll go into next Monday. So, no in-person lab this week, no in-person lab next week, but there is an out-of-class lab. Then the week after that is test 2, which also won't be a lab. We won't have a normal in-person lab again until the last week of class, 22nd through 25th. But as we approach test 2, we will take time to review for it. I plan on taking about a week to talk about waves from between now and next Wednesday to Friday, and then we will be reviewing it for test 2, like we did with test 1, which also will take place during lab, so we still have lecture that week to make sure everyone's feeling comfortable with it before the actual test. How does all of that sound before we move on to anything else? All right. Any other questions, thoughts, needs, concerns, etc. before we start talking about waves? All right. Now, if you've been noting which chapter numbers we've been using out of the course, the book this course is based on, we're skipping around a lot. We just covered pressure and similar topics, which the source book calls 13 and 14. We are now skipping all the way to what the source book calls 19 and 20. There's some bits in the middle there that just aren't on this course's syllabus. So if the numbering on Brightspace is weird, that's why. Don't worry. Oh, it's right. I have to download my most recent notes. So for the next week or so, we will be discussing waves, which in my opinion is a pretty important topic, given that 2 to 3 common human senses are based on wave mechanics. Sight and sound being the main 2, but your sense of touch, if you can feel waves other than light and sound as well. Change that slide, whoops. All right, so once again, the source book calls this chapter 19. We'll be discussing this type of wave, as well as just waves as a whole. Anything that can be categorized as a wave, I want to at least mention in this section. Now, as we like to do in this class, I want to define what it is we're actually discussing in as concrete terms as possible. And before I define waves, I actually need to define the thing that waves are made of, because waves are kind of a combination of topics all working together. So before defining waves, we're going to look at what forms a wave, and that is simply a vibration. So to define vibrations in terms of the physics definition, vibrations, more scientifically referred to as simple harmonic oscillations. Oscillation is just a specific word for a repeated constant motion back and forth between 2 points. If something is oscillating, it's doing the same thing over and over again between 2 fixed points in space. And there are a lot of different things that you can describe as vibrations and or oscillations. Again, any constant repeated motion can fall under this definition. For example, this device that I have just now constructed can be called an oscillator, because it's going to oscillate back and forth between 2 points. It's just a spring with a weight hanging from it. And right now it's meant to kind of be in its base default state. The spring has been extended. There's some energy stored in the spring. Elastic objects tend to hold on to energy when they're stretched. So there's energy stored in the spring. The weight even has some GPE since it's some elevation above the ground. I'm pointing out the energy types here because they'll be relevant in a minute. Right now, this thing is, I wouldn't call it oscillating very strongly. It's moving just a little bit because I can't get it to completely stop. But if I really wanted to start oscillating, I'm going to take hold of the mass, pull it some distance away from its baseline configuration, and let it start again. That was too strong. Sometimes if things oscillate too much, they break. And that's what happens when you scream at a wine glass until it shatters. More on that later. A little less this time. Now this is oscillating, which is to say bouncing back and forth between two roughly fixed points. A high point oscillating down past the baseline point to the low point, and then oscillating back up through the baseline point to the high point, constantly ad infinitum until it runs out of energy. That is, at its core, what a vibration is. Constant motion back and forth. About anything is capable of undergoing this type of motion. Here I have an oscillator like the one I have currently going in the front of the room. Pendulums count as well. That is just the technical term for something undergoing this motion. All of my markers are falling off the desk. This also counts as an oscillation because the pendulum bob is moving back and forth between two fixed points. So technically, scientifically, this is the same as that. Same concepts. But again, any vibrating object is basically doing the same thing. This image right here is what happens when you resonate a wine glass. This is what opera singers do when they're feeling fancy. If you sing at the glass at just the right frequency, the glass itself will start vibrating. Its different pieces will flex constantly between two main positions. You can kind of see it shaking here between one extended state in this axis and one extended state in this axis. And the vibrations just keep increasing until it physically cannot contain the energy anymore and it shatters. So there's science behind how this happens, if you're familiar with this particular trick that singers can perform. Questions so far? All right. So these are the properties of oscillations / vibrations. And because we like math and physics, let's look at some of the mathematical things that we measure regarding vibrations and oscillations. Got 3 vocab words for you right now. 3 things that you can measure about vibrations and oscillations. First up, you can measure a vibration's amplitude. This is basically just the term for how big is the vibration, how strongly is something vibrating. The amplitude of an oscillation vibration is simply how far from baseline is it currently oscillating between. I've reset this now back to its baseline configuration. This is the height that it sits at when it is not oscillating. If I pull it down by about 2 centimeters, it's now going to constantly oscillate between 2 centimeters below baseline and 2 centimeters above baseline. And so 2 centimeters would be the amplitude of this oscillation. It's just a very specific distance measurement. And I want to point out amplitude is always distance from baseline, not the distance from full top and full bottom. Amplitude tells you how big the vibration is, and to do that you have to factor in where is the object normally versus what 2 fixed points is it shaking between. So amplitude is either baseline to highest point or baseline to lowest point. It is not low point to high point. Is that clear? Now again, it is just a very specific distance measurement. So if I disturb this 2 centimeters from baseline, the amplitude is 2 centimeters. It's just, again, distance, measure it in meters or some variant thereof. The second measurement that you can take regarding vibrations is that vibration's frequency. Are you familiar with the term frequency being used to apply to sound waves, for instance? All right, good, just checking. Now the definition of frequency is how frequently something is happening. When you measure something's frequency, what you're measuring is how many times an event takes place in 1 second. In physics, well, actually, I don't think there is another unit for frequency that I've commonly heard used. The unit for frequency is hertz, spelled like this, named after one Heinrich Hertz. And the definition of 1 hertz is one event taking place every 1 second. If something happens once every 1 second, that event is taking place at a frequency of 1/1 seconds, which is 1 hertz. If something takes place twice per second, that's 2 hertz. 2 events per 1 second. 3 events per second is 3 hertz, so on and so forth. So the higher something's frequency is, the more frequently it is happening. That's how I remember it anyway. So anytime you've heard frequency or hertz, that's what it's referring to. Any measurement of frequency, that's all this is, whether you're talking about sound or some other thing that is currently undergoing some repeated action. Hertz, the full word is H-E-R-T-Z, it is German. The abbreviation is just Hz. And because frequencies tend to get pretty big, you'll often find things listed in like kilohertz or megahertz or possibly even gigahertz. The frequency measurements can get kind of big depending on what you're measuring. Now, related to frequency, but technically a distinct measurement, is the period of oscillation. This is a related concept. Within physics sciences, the term period refers to the number of seconds it takes for one repeating event to transpire. If it takes 1 second for this pendulum, well, I'll make it a pendulum. If it takes 1 second for this pendulum to go back and forth, then the period of this oscillation is 1 second. If it takes it 2 seconds to go back and forth, that period of oscillation is instead 2 seconds. It's the time it takes for one event to transpire. And since it's a time measurement, it's just measured in normal seconds. So no new unit on that one. The variable for that is uppercase T. It's basically a more specific measurement of time. So it uses T, but it's uppercase instead of lowercase. And you might have noticed, period of oscillation is the time it takes for one event to occur. Meanwhile, frequency is the number of times that event occurs in 1 second. Period and frequency are inverses of one another. 1 hertz is defined as 1 event per 1 second. And then period of oscillation is defined as the number of seconds per event. They're the same measurement, just upside down. We just call them 2 different things because the 2 concepts were probably used at 2 different points in history in 2 different places. They tell you basically the same information, just from a slightly different perspective. But because they are inverses, if something has a high frequency, it will likely have a low period of oscillation. You know, a 3 hertz vibration, the period would be 1/3 instead of 3/1. So 3 hertz would be 1/3 seconds per oscillation. Likewise, if something's period of oscillation is 3 seconds, if it takes 3 whole seconds for one event to pass, then the frequency calculation would be 1 event per 3 seconds. 1 second period translates to 1/3 hertz. They are inverses. If one gets bigger, the other gets smaller. Does that sound all right? All right. Those are the 3 main things that we use to measure vibrations. Again, amplitude is their size, frequency is how often the vibration takes place, period is how many seconds it takes one vibration to pass. To practice this information, let's put some numbers to this example. If I make this oscillate again. Note the oscillating spring to that one's to the left, that picture's to the right. Note the oscillating spring. My formatting's messed up. Pardon, sorry. From its baseline, it is pulled 10 centimeters upward and allowed to oscillate between 10 centimeters above baseline down to 10 centimeters below baseline and back. The process of the oscillator completing one full oscillation, and one full oscillation would be the time it takes to, say, go from top, down, and back to top. That is one complete cycle. The time for one complete cycle is 2 seconds. Given all this information, first question, what is the amplitude of this vibration? A little louder. 2 centimeters. 2 centimeters is the distance it was pulled from baseline, and that is the maximum distance it ever errs from the baseline. It's not 4 centimeters, not the distance from lowest point to highest point. It's the distance from baseline to fully extended in either direction. So the 2 centimeters is the amplitude. Next, what is the frequency of this vibration? Not quite. The definition of frequency is how many events take place in how many seconds. The data we have here says that one full oscillation, one event, takes place every 2 seconds. So frequency, one event takes place every 2 seconds. That is half a hertz. Half a hertz means that in 1 second, only half of the event has transpired. Is that all right? Okay, now the inverse, what would the period of this vibration be? 2, very good. It takes 2 seconds for one event to transpire, therefore 2 seconds per one event, period is 2. Note again, these are inverses of one another. If you know one, you just flip it and you get the other. First part sound okay?
Is the amplitude supposed to be 10 centimeters?
Wow. Yes, it is supposed to be 10 centimeters. I must have been saying 2 because that got stuck in my head from earlier. I am so sorry. 10 centimeters is the amplitude. This clearly demonstrates that I am both tired and dehydrated. I apologize. Yes, it's pulled 10 centimeters up and allowed to oscillate between 10 centimeters up and 10 centimeters down. Therefore, the amplitude is 10 centimeters. I am so sorry. Please call me out when I do things like that. Yes, amplitude is 10. I am dehydrated. Your brain doesn't work as good when it doesn't have water in it. Thank you. Any other questions or corrections from the first part? All right. Separate question now. The pistons inside of a car engine can get so fast that they complete 120 full oscillations in 1 second. If you're unfamiliar with internal combustion engines, most car engines have pistons. You explode a tiny amount of gasoline inside of the piston. That explosion pushes the piston out, and then various pressure differences pull the piston back in time for the next explosion to push it back out. So there's a constant in and out motion of the cylinder of the piston, and that motion is then translated into the wheels of your car. And this particular engine is firing 120 full oscillations in 1 second. What is the period of that oscillation, and separately, what is the frequency of this oscillation? Very good. Frequency, we got 120 events per 1 second. Therefore, frequency is 120 hertz. Period, we have 1 second per 120 events. Therefore, it would be the inverse of, it would be 1 divided by 120, which is less than 0.1. .0083 repeating seconds, which means that is the number of seconds it takes for the cylinder to explode, be pushed out, and then for the pressure to pull it back in, ready for the next explosion. These things are fast. Again, thing to remember, period and frequency are inverses. If one of them's really big, the other will be really small. Sound good? Questions? All right. Now, we're going to start tying all of this into waves and wave behaviors that you should be familiar with, given possibly multiple of your senses rely on waves, and you've probably observed waves in other formats before. First up, I'd actually like to draw attention to something on this image that I haven't pointed out consciously yet. This image is meant to represent this action taking place over time. So a bob oscillating up and down on the end of a spring, and the images scaling from left to right represent the passage of time. It starts up here, goes down, bottoms out, goes back up, tops out, constantly cycling between those 2 points. And the blue sine wave, sine spelled like this, that blue wave shape formed from the motion of that particular bob over time kind of looks like a wave, or at least the basic shape that people tend to think of waves taking, correct? Mathematically, we call this pattern a sine wave because it's created by inputting the sine equation into your graphing calculator. We spell the full word like this, but the button on your calculator takes the E off, if you haven't used that in a minute. This is why we use this pattern to represent waves a lot of the time, because this pattern represents the motion of an oscillating object over time, and since waves are made of traveling vibrations, that means that this pattern also represents wave motion pretty well. So this pattern is going to keep showing up, this sine wave curve. And that's why we keep drawing them like this. Make sense? Okay. So to kind of hint at what to fully define what I just said, we've defined vibrations, and now we're going to define waves. Waves are traveling vibrations. That oscillator over there is oscillating back and forth in place. The object is moving up and down, but the spring isn't going anywhere. The mass itself doesn't really leave the position that it's in. And therefore, its constant energy transformations aren't going anywhere either. as this thing shakes up and down, there's a lot of energy transferring and transforming going on here. I kind of mentioned a second ago that there's stored elastic energy in the spring. The mass has GPE because it's capable of falling from this position. At various points in time, it even has kinetic energy because it's moving. The act of again, drink your water. The act of vibrating or oscillating requires energy to constantly be transforming and transferring between different parts of the system. Sometimes the spring has it stored, sometimes the mass has it as kinetic. The energy is just constantly moving between positions of this object and between different states. But the energy never leaves this area in the case of just a normal vibration. Yeah, the spring might have it one moment and the mass might have it the other, but it's still contained in this general region of space, within just this one region of oscillating object. What waves do is they take that vibration, they take that energy exchange, and they send it somewhere else. A wave is just a traveling vibration. And since vibrations are constantly transforming energy, that means that waves are also made of traveling energy. I want to note, though, that all forms of waves, and we're going to talk about loads of different types of waves, both ocean and otherwise. All types of waves, the vibration is what is traveling. The object that is vibrating is not what is traveling from one point to another. What do I mean by that? Currently on screen right now is a repeating image of a spring with a wave traveling through it. So that's just a very long spring coil. Someone has shaken one end of it and a wave is traveling from one side to the other. I'm going to try to replicate it now with this spring. I might need to find a longer one, but let's see if I can get it working. So I'm going to do something similar. I'm going to pluck this spring coil that is going to put energy into it. It's going to start vibrating, and that vibration is going to travel along the length of the spring. So technically what you're seeing here, and I do need to find a longer spring. Technically what you're seeing here is the vibration, and only the vibration, traveling from one part of the spring to the other. What this image is trying to show is this hand is currently trying to highlight just one coil on that spring. I'm going to try to make the picture a little bigger now. The artist behind this image is using that hand and that highlighted section to just draw your attention to one very specific coil on that spring. All springs are made of a certain fixed number of coils. Waves are made of traveling vibrations. A vibration is traveling from this end of the spring to the other. And as that vibration travels through this section of the spring, it does make that particular coil vibrate. That coil undergoes a similar motion as we've been talking about. From its baseline, it goes up and back. But note that as the vibration goes from one end to the other, that coil does vibrate up to down, but that coil isn't traveling with the wave. That coil does shake, but it always returns back to its original position even as the wave continues past it. Does that make sense? That one coil doesn't zoom to the end of the spring. Only the wave itself, only the energy zooms from one end of the spring to the other. The coil goes back to its origin point. It has to return to its baseline. I'm telling you this to try to point out and solidify the concept that waves are traveling vibrations, waves are traveling energy. The vibration and the energy is the only thing that actually goes from point A to point B. When waves travel through something, we call that traveling through a medium. When you think of common wave types, most waves that you tend to think of involve a medium that the wave travels through. In this particular case, the wave is traveling through a spring. That is the medium through which the vibration takes place. But loads of other waves also have mediums. I think the best example is sound. Sound requires the medium of the air between us for the sound to actually be able to travel. If you've ever heard that there's no sound in space, it's because there's no air in space. Sound waves require air to be able to travel through them, like how this spring, this wave requires the spring in order for the wave to travel. If I have a spring and I send a wave from one side to the other, the spring needs to be there for that to take place. If I hold my hands out without the spring between them and do the same motion, nothing happens. This particular wave requires the spring in order to travel, like how sound requires air to travel. Ocean waves require water to travel. Earthquakes require earth to travel. Earthquakes are just waves, if you weren't familiar with that. Waves have mediums. Waves are made of vibrations and energy that is traveling through that medium. And as the wave passes through a specific spot of that medium, that specific spot does vibrate, as you can see here. But it stops vibrating once the wave has traveled completely through that spot. The energy goes from point A to point B. The medium only shakes as the energy is in that particular part of the medium. Does that sound all right? The medium itself will always return to a baseline state after the energy has passed through that particular spot. To point out some evidence of this in the real world, I'm going to tap ahead again so that you can see the picture a little more clearly. Bless you. Evidence in the real world that waves are traveling vibrations and traveling energy that don't bring their mediums with them. I mentioned a second ago that sound waves require the medium of the air. And sound is just a vibration, basically a little energy ripple through the air from my vocal cords to your eardrums. Every time I speak, I'm putting energy into the air, making the air shake, and that ripple travels through the air to get to your ear, like how literal water ripple travels out from throwing a rock in the pond, for example. But the sound doesn't carry all of the air that it travels through with it. It just makes the air in a localized spot shake for a second, and then that air goes back to normal as the wave moves through that position. If the sound wave brought all of that air with it, every time you spoke, you'd be creating a gale force wind as your sound waves bring all the air that they travel through out away from your throat to whoever you are talking to. The air doesn't go with the sound wave, it's just a material that the wave can propagate through. The air will vibrate for a sec as the wave moves through that specific spot, but then it'll go back to normal. Really big, really loud sounds can make the air shake a lot, but human speech, it shakes just a tiny bit and then it's done. Other examples would be ocean waves don't bring the entire ocean to shore. They only really churn up the water that's at the shoreline. So, unless it's a really big tidal wave, which is kind of the exception to this rule, when a wave hits the shore, it's not bringing water from the ocean to the coastline. That energy is just churning up the water that's already at the coastline and slamming it back down. And similarly, earthquakes don't bring all of the earth with them. They just make the earth in a spot shake until the energy travels through it. Make sense? Does that not make sense? Let me say it like that. Okay, so waves are made of traveling vibrations, made of traveling energy. Since waves are made of vibrations, they also have amplitude, frequency, and period of oscillation, just like vibrations do. So all three of those things we talked about a second ago for vibrations and oscillations, they also apply to waves. But because waves are traveling, because they can go from point A to point B and carry their energy with them, there's a couple other variables about them that we can measure that I want to talk about today so that we can use them next time. First up, I want to draw attention to the fact that waves have crests and troughs. It's kind of hard to see for a normal oscillator because since it's only going back and forth between two fixed points, you can see the low point and the high point, but you can't see them kind of coexisting at the same time unless you draw it out over time. But a waveform shows what's happening over time, shows what's happening as the wave travels, and a continuous wave can make the medium it's traveling through take this shape. So when the wave is all drawn out like this, you can see all of the peaks lined up together and all of the low points lined up together. We call those high points crests, and we call those low points troughs. You could also call them peaks and valleys. That's an accurate term for it, but I want to make sure you're familiar with the vocab of crest and trough. Crests are still one amplitude above baseline. Troughs are one amplitude below baseline. Make sense? All right, so kind of just a specific application of amplitude is all crests and troughs are. Two newish things about waves that I want to make sure you can measure though is first, wavelength. Vibrations don't really have length. They only shake back and forth between two fixed positions. But waves, proper traveling waves, have wavelength, which is the distance of one full wave. You can also think of it as the distance that the wave travels in one full oscillation. If you were watching waves at the beach, you could hypothetically pause time and see the water taking this pattern. If you then went over to the waves on the water, took measuring tape, and physically measured the length of one full wave from here to here, that is the literal wavelength. It is the length of one full wave, the distance it covers in one full oscillation. Which you can see for waves, since they travel, it's harder to visualize for just an oscillator moving back and forth in place. So when I say wavelength, I do literally mean how long is the wave in question, physical length. And since this is just another very specific distance measurement, it's just measured in meters. It doesn't have a new unit. It does have its own symbol though. This is the Greek letter gamma? Or is it lambda? I can never remember. I think it's lambda. It's lambda. So the variable for wavelength is lowercase lambda. Kind of looks like a weird inverted flipped letter Y. And since waves travel, they not only have wavelength, they also have velocity. Since waves travel from point A to point B, velocity, wave speed, is just the measurement of how quickly it moves from point A to point B. Same old velocity measurement we've been using, but since they're traveling, we can measure that unlike a static vibration. Make sense? Okay. Wave speed is where we get concepts like the speed of sound, for example. Most types of waves have a specific fixed velocity as long as it's the same wave type. All sound waves travel at the same speed through the same type of air. And this causes an interesting relationship between wavelength and wave frequency. This is the concept, well, one of the things we'll be exploring on Friday. I'm just kind of introducing it before we break for the day. Waves have velocity, and the velocity of that wave is actually tied to both its frequency and its wavelength. Frequency is the number of waves that travel every 1 second. Meanwhile, wavelength is the distance of one full wave. Therefore, when you multiply frequency times wavelength, you are multiplying waves per second times the distance of a single wave. And therefore, that will tell you the distance the wave travels per second. Number of waves times wavelength will tell you the distance traveled, the number of wavelengths it goes through in a certain amount of time, because frequency is events per time, therefore there is a divided by seconds already in there inherently. So wavelength times frequency is wave velocity. And this causes some very interesting things related to the human perception of things like sound and light. And that'll be the start of what we're exploring the next couple of days. How we feel? So that's all the stuff that we measure about waves. We'll practice all of that and talk about what it means for life on Earth next time. Any questions, needs, etc. before we break? All right. In that case, excuse me, please have a wonderful day. Please let me know if you need anything. No lab this week or today. And again, if you want to watch the eclipse next week, make sure you grab a pair of these. I'll leave these here on the table until up to and including next Monday. Grab a pair and have a great day.